This is an introduction to optimization, chi-squared, and least squares fitting, also known as curve fitting. You will be doing a lot of this during this laboratory to get parameters out of the data you'll be taking. A quick point here, that's chi-squared, the Greek letter chi. It's not a Latin X, so please say it correctly. So here's our problem. We get some data, and let's say it looks like this. That's more or less a straight line. So if I want to get some parameters out of that, I can say, well, there's one point there, there's another point there, let's draw a line. And the equation for a line is, of course, y equals mx plus b. M is the slope and b is the y-intercept. Well, my y-intercept is right there, that's b. Slope is rise over run, there's m. And there are my parameters. In this case, the slope is about 2, my y-intercept is about 8. Great. But there's a problem with this. I'm only using 2 of my data points. I've got a whole bunch of other data points that I'm just basically throwing away. It would be better if I could find some way of getting a fit where I'm using all of my data points. How can I do that? Well, instead of just using the first and the last data point, I can imagine sort of eyeballing a line that would go evenly through all of these data points. Something like that. That's better. I can then recalculate a new m and a new b, and I'll have better parameters. Of course, I really don't want to do that. I want the computer to do all this. How could I write an algorithm so that the computer would select the best possible fit for this data? So the first thing I've got to do is to quantify how good my fit is. Well, there's the equation I'm trying to fit it to, and let's just draw a random line. Now, clearly, that's a lousy fit, but how lousy is it? Well, I'm going to take the difference from the line that I drew to each of my individual data points. I want to square each of those values and add them together. This is a quantity that we call chi-squared, and it's a measure of how good or bad my fit is. The worse my fit, the larger the value of chi-squared is going to be. If I use a different line, for example this one, I'll get a slightly smaller value of chi-squared, and hence a slightly better fit. A brief aside, there are other ways to define chi-squared, but they all amount to the same basic principle. This method is simply the simplest way to define chi-squared. This brings us to a new way to visualize the quality of my fit. I can think of chi-squared as a function of the slope. So there's one line, a pretty bad one, but I can calculate the chi-squared associated with it. I draw a second line, calculate the chi-squared of that, and so on. Now I can see chi-squared as a function of m. The minimum value of chi-squared gives me the m value that I want. In this case, about 2. Of course, in this example, chi-squared is not only a function of the slope, m, but also of the y-intercept, b. So chi-squared is best thought of as a surface, a two-dimensional function that is a function of both b and m. In this case, the best fit is again an m of about 2 and a b of about 8. But it's still visualized as being the low point of this two-dimensional surface. So now I have these two ways of thinking about chi-squared. I can think of it in terms of the data space, that is, the best line through my data points, or I can think of it in terms of chi-squared space, that is, this two-dimensional surface that is a function of b and m. In this case, the best fit is the low point of this surface. So now let's set aside the data space and just think in terms of the chi-squared space. How do I actually go about finding the minimum value of chi-squared? Well, the straightforward approach would be a so-called grid search. That is, I'll just try a whole bunch of different values of m and a whole bunch of different values of b and just see which one gives me the best fit. That is, the lowest value of chi-squared. Well, it turns out that's not a really good way of doing it. Calculating chi-squared is relatively expensive. It takes a lot of time. Consider this. I could have hundreds or even thousands of data points that I'm trying to fit, and my function could well be a lot more complicated than a simple straight line. Every time you calculate chi-squared, you have to calculate that same function over and over again. Even if you have a supercomputer, that could take too much time. So we can't do a grid search. We need a faster way of solving the problem. So our game is this. We have to find the minimum value of chi-squared while evaluating chi-squared as few times as possible. How can we do this? Remember, we cannot see the full function. We only see each point at which we actually do our calculation. So our job is sort of that of a blind man trying to feel his way to find the lowest point of this surface. How do we do that? Well, we're going to try a starting guess, just some random value of m and some random value of b. Now at that point, I want to evaluate the function a couple more times to find the gradient at that point. That is, how steep is the surface at that point and which way is it sloping downward? Now, we just feel our way downhill until we get to the bottom. Go in that direction, try it again, find our way down, keep going downhill until we get to the point where the gradient is 0. At that point we found the minimum value and we found our minimum value of chi-squared. And we've done it by only evaluating chi-squared a very few number of times. Let's consider a different function, a bit more complicated this time. Here's my data. Now, any reasonably intelligent primate can look at that data and say, there's a peak right there. Now, I can fit this peak with the following function. This is a so-called Gaussian function. And in this case, p gives me the position of the curve, and a gives me the amplitude, the height of the peak. Now, how would we go about thinking of this in terms of chi-squared space? If we think about this problem in terms of chi-squared space, the chi-squared space is going to look something like this. To solve this, we first have a starting guess, and we work our way downward. Find the minimum value, plot that out, and voila, we've got our fit. Great. However, suppose we had a starting guess somewhere else. We work our way downward, but we find a different minimum. Something like that. Now we've missed our solution. Or we can have an initial starting guess right here, say, and as we feel our way downhill, we end up wandering off the map entirely, and we end up having a divergent solution like so. Bad. Hence, if we have poor initial guesses, we will not get the actual best fit of the curve. If you end up doing a chi-squared fit and you get a nonsensical result, your best bet is to try better initial parameters. So, how does this work in practice? Let me illustrate that using the Capstone software that you'll be using throughout this laboratory. First, acquire some data, as I've done here. Then, select which curve you want to use to apply a fit. Click on the icon here. That will bring you a pull-down menu that will give you a selection of different curves to fit it with. In this case, we'll fit it with a quadratic curve. That's checked. And then we have our fit. Here you see the equation we have applied, at squared plus bet plus c, and the various results of our parameters, a, b, and c, and the corresponding uncertainties. If by chance this does not give us a good fit, we would have the option of selecting the curve fit editor that you find here. Clicking on that, we would then be able to change our initial guesses for the three parameters, a, b, and c. Often you will find this is not necessary. The random guesses provided by the program will work just fine. But if necessary, you can change the initial guesses here. You also have the option of writing a custom function in case the list of functions provided by the Passcode program aren't suitable to your problem. That's it. It's really pretty simple. First, acquire your data, then select the appropriate function to fit your data, or if necessary, write a custom function. If necessary, adjust the initial guesses and try again until you get a good fit. That's all there is to it. My purpose here has not been to go into all the nasty details on how least squares fitting actually works, but give you an appreciation for what's going on underneath the hood inside the computer so you can better use the tools available to you.